You know, for basically all of human history, we've learned about the universe by looking up, by seeing. But what if we could also listen to it? What if we could actually feel the most violent cosmic events stretching and squeezing the very fabric of space-time around us? Well, that's the incredible story we're diving into today. So picture this. It's 5:51 in the morning Eastern Time. Two huge L-shaped machines, one in Washington State, the other all the way over in Louisiana, they both record this tiny, perfect signal. Now, this wasn't an earthquake, wasn't a truck rumbling by. No, this was something else entirely. Something that had been traveling across the universe for over 1 billion years just to get here.
And that single moment, wow, it was absolutely monumental. It was like our species suddenly evolved a brand new sense. For centuries, we've been building better and better eyes to see the cosmos, from Galileo's first telescope to Hubble. But on that day, we finally built ears. For the first time, we could actually listen to the symphony of the universe.
And let me be clear, this wasn't just another cool discovery. This was the dawn of a whole new way of doing astronomy. A new key to unlock some of the universe's most extreme and hidden secrets.
But to really get what this is all about, we've got to rewind the clock, way back, about 100 years, to a guy you've probably heard of. Because this entire field, this whole new sense, it didn't start in an observatory. It started in the mind of Albert Einstein, as this wild, mind-bending prediction of his general theory of relativity.
So what are these things? Well, imagine space-time, the 3 dimensions of space and 1 of time. Imagine it's like the surface of a pond. Now, if you have something incredibly massive and dense, like 2 black holes, and they start spiraling into each other, they create ripples. But here's the crazy part. These aren't ripples moving on the pond. They are ripples of the pond itself. And that's the key distinction, the thing that makes this so wild. Think about light or sound. They travel through space, right? Like a boat moving on the water. Gravitational waves are totally different. They are waves of space. As a wave passes by you, the distance between 2 points literally stretches, and then it squeezes. Space itself is oscillating. It's the medium and the message all in one. Now, this idea was so bizarre that even Einstein himself wasn't totally sure if they were real or if they'd be too faint to ever find. And that uncertainty kicked off a century-long hunt, a story filled with doubt, with brilliant arguments, and just incredible persistence to find something many people thought was completely impossible to detect.
So the hunt starts way back in 1916 with Einstein's prediction. And for decades, it was just theory. Then, in 1974, we got our first tantalizing clue. Hulse and Taylor found 2 neutron stars spiraling into each other, and they were losing energy at exactly the rate Einstein's theory predicted they would if they were emitting gravitational waves. It was the first indirect proof, and it won them a Nobel Prize. But it took another 40 years of unbelievable effort before LIGO finally heard that first chirp and gave us the first direct detection in 2015. The hunt was over.
So why did it take so long? Well, the simple reason is that the effect of these waves, by the time they get to us, is almost unimaginably small. I mean, trying to detect a gravitational wave is, without a doubt, one of the most difficult and precise measurements humanity has ever even attempted. The strain, that's the amount that space is stretched by a typical wave that hits Earth, is about 10 to the minus 21. Now, that's a 1 with 20 zeros in front of it. It's a ridiculously tiny number. So what does that even mean in the real world? Yeah, that's what it means. You're trying to measure a change in distance over several kilometers. That is 1,000 times smaller than a single proton. That's the challenge. It is an absurdly, beautifully, mind-bogglingly precise measurement.
So how on earth do you even do that? Well, with this incredibly clever machine called a laser interferometer. Here's how LIGO works. You take a powerful laser and you split it in 2. Each beam travels down one of these 4-kilometer-long arms. They bounce off these perfectly polished mirrors at the end and come back. Now, if the arms are exactly the same length, the 2 light waves come back and they cancel each other out perfectly. The detector sees nothing but darkness. But, and here's the genius part, if a gravitational wave passes through, it stretches one arm and it squeezes the other one, just for an instant. That tiny change means the light beams fall out of sync, and for a split second, the detector sees a flicker of light. That little flicker, that's the sound of the universe. And with that first flicker, a revolution began. In just a few years since 2015, we've gone from 1 single detection to now over 200 of them.
and every single one is teaching us something new, something profound, about the most extreme and violent objects in the entire cosmos. Let's just run through a few of the greatest hits, shall we? You've got GW 150914, the OG, the very first detection. That was two black holes smashing together, and it proved for the first time that they actually exist in pairs. Then there was GW 170117, an absolute game changer. That was two neutron stars merging. We saw it with both gravitational waves and with light. Another one, GW 190521, created a whole new class of intermediate black hole we didn't even know existed. And some of the recent signals have been so crisp, so clear, that we're using them to test fundamental theories from Einstein and even Stephen Hawking. And just to give you a sense of the sheer power we're talking about, look at this. In that very first detection, an amount of mass equal to 3 of our suns was converted instantly into pure energy. For a fraction of a second, that single distant event was more powerful. It outshone every single star in the entire observable universe combined. It's just staggering.
And that neutron star merger, GW 170817, it was like finding a scientific treasure chest. In one single event, we confirmed what causes short gamma-ray bursts. We proved that gravity travels at the speed of light. We literally watched the universe forging heavy elements like gold and platinum in real time. And we even found a whole new way to measure the expansion of the universe. It officially kicked off the era of multi-messenger astronomy, where we can see and hear the cosmos at the exact same time.
And believe it or not, this is just the beginning. The detectors we have now, they open the door. But the next generation of instruments, they're going to blow that door wide open, letting us listen in on a whole new set of cosmic conversations. So on the ground, we're planning detectors like the Einstein telescope with arms 10 kilometers long. But the really huge leap is going to space. The LISA mission will be 3 spacecraft flying in formation, creating a giant triangle with arms that are 2.5 million kilometers long. It's incredible. See, if LIGO hears the high-frequency shouts of the universe, like black holes colliding, LISA is designed to hear the deep, low-frequency murmurs, like the slow dance of supermassive black holes at the centers of colliding galaxies. And with these new, more sensitive ears, we can start to tackle some of the absolute deepest mysteries in all of science. What is matter actually like inside the crushed core of a neutron star? How did those giant black holes in the middle of galaxies get so ridiculously big? We might even, just maybe, hear the echo of the Big Bang itself, the primordial gravitational waves from the very first moments of creation. We have truly opened an entirely new window onto the cosmos. For 100 years, we strained just to hear a single, fleeting whisper. Now, those whispers are turning into a roar, and they're revealing a universe that is stranger, more violent, and way more magnificent than we ever dared to imagine. The only question now is, what other secrets is it waiting to tell us?